Welcome to this new web note on uh, vector spaces and properties of object defined on vector spaces. So we have seen that in some cases we have a norm defined on a vector space which allows for in a natural way for a distance to be defined or generated from the norm. And then of course normal vector spaces, they become what? Metric spaces. There are examples for which, very interesting examples for which this property fails. And let us start with that example. So as a motivation to this semi-normal vector spaces web note, okay? So example, let us take continuous functions, but not on a compact set of R, but on the entire set R. So we take V to be the continuous functions on R into R. So the problem here is the boundedness. So of course this is not empty because we have the zero function, and we do have all polynomials defined on R. They are all continuous on R. So this is a very well defined set, and because the sum of every two continuous functions is continuous, the multiplication by a number is still continuous, therefore V is a vector space. Okay, V is a vector space. Now the problem is if we take continuous functions on a compact set of R, meaning an interval, then we have a Banach space, and we have seen this as one of the examples of normed vector spaces, a classical example of normed vector spaces. The problem here is that functions defined from R into R are not bounded, continuous, are not bounded necessarily. And if we take let I be a closed interval, okay, closed be a closed interval, or any compact set in fact, then we can define the quantity pi of f to be the sup of f of x when x belongs to I. And what's happening here is that this sup is very well defined because your function is bounded and it satisfies. It is clear that the function pi, which is defined from v into the positive numbers, has all the properties of a norm, okay? But the problem is, in other words, the triangular inequality and everything, the only problem is that it fails one very important property, that pi of f equals 0. This does not necessarily imply that f equals 0. In fact, we have the following, is that if pi of f is equal to 0, if and only if f is equal to 0 on I, in other words, f of x is equal to 0 for x in I. So the function f vanishes or identically equal to 0 on the interval I, but it doesn't mean that the function is equal to 0 everywhere. I mean, so this is number one. Number two, so it fails. So this is a terrible property. But what's interesting is that if f is not equal to 0, I'm talking about the continuous function defined on the entire R, so we can find an interval, closed interval, okay, such that pi of f is not equal to 0. Okay? So here, of course, we have plenty of intervals, and also we can do one more thing that I would like to point out here before we move on to the general case is that one more thing is that if we look at now the family, okay, so we look at the family of all intervals, the family of all closed intervals, okay, on the real line, okay. So in this case, somehow we can restrict, instead of taking all the closed intervals, can be reduced, okay, and generate the same information to a countable family of closed intervals. And in this case, of course, the family is the family of the minus n to n greater than 1. So you see, we have a countable family, and we have now a countable of family function. So we'll have, instead of writing p of minus n, we will only write p of n. So again, what is p of n of f? It is the sup of absolute value of f of x when x here is between minus n and n. So this will capture also the property that we said that if f is not equal to 0, then we have be careful, someone may be tempted to have the sup of the Pn of f to try to cheat and generate a norm, but this will not be valid because this may become infinite, since this will give us the sup of f of x over the entire real line, and we know that in that case the function can be n-bounded. Okay, so now what is the general case? So we have this example. Okay, so we have a vector space, and we have this kind of functions p that satisfy some nice properties like the norm. Okay, and so we call them seminorm. So here we have this seminorm object. Okay, so we have let V be a vector space. And we consider P that goes from V into 0 plus infinity, such that, okay, number one, P of 0 is equal to 0. Number two, P of lambda V is equal to absolute value of lambda P of V. And this is, of course, for every V in V and every lambda in R. And finally, the triangle inequality, 3, P of V plus W is less or equal to P of V plus P of W. So this is, we say that P is a seminorm defined on V. Okay, so again, what fails, we said, is the fact that in general we do not have, so here, okay, we do not have, so what's new or what's different from a norm, we do not have P of V equals 0 implies V equals 0. So this we do not have. Okay? Great. So once we have this, it's very easy. Remark, using the properties of P, of course, to see that we have for any V and W in V, it's very easy from the triangle inequality, like we did for the norm, that P of V minus P of W absolute value is less than P of V minus W. Next, we discuss the concept of topology. Okay, so let us see how topology defined on a vector space for which we have seminorm. Okay, how can we define naturally as we did for the norm? How can we define the topology? And exactly in a similar fashion, we introduce what we call the P-balls. Okay, so here we define the concept of P-balls, open and closed. So we have B open V R to be the set of V W in the vector space such that P of V minus W is less than R. And we can also define the closest one, which is VR equal W in V such that P of V minus W less or equal than R. For the purpose of topology, we focus, of course, only on the open balls here. Okay? So this implies, because of the properties of P, that in fact, for any V and R, we have B, and the same property is valid for both open and close, and therefore I'm going to drop the C and the O. The ball centered in V with radius R is just V plus translation of R time the ball centered in 0 with radius 1. So these are direct from the properties of the seminorm P. Okay? And in that reason, so we can focus basically on the unit open ball or the unit closed ball. And this is now, let's call it M. Set notation, set M throughout to P the open ball 0, 1, which is W in V such that P of W less than 1. And whatever we say on this open ball, the properties of M are the same for the closed ball. They satisfy the same. So the first one, first property, is that 0 belongs to M. Okay, so property 1. Okay, 0 belongs to M, which means that the set M is not empty, and M is convex. So the property here, when I say property number 1, the property that interests me here is the convexity of the set M. So indeed, it's not very hard to see this. Indeed, let V1, V2 in M and alpha between 0 and 1, then P of alpha V1 plus 1 minus alpha V2 is less or equal from the triangle inequality P alpha V1 plus P1 minus alpha V2, and this is equal to alpha P of V1 plus 1 minus alpha P of V2 from property number 2, and because everything is positive, which is less than 1. So indeed, alpha V1 plus 1 minus alpha V2 belongs to M, and that is the definition for a convex set. So to be convex, you need to have the entire segment, which means exactly what we just proved. The next property, 2, M is absorbent. Sorry, not absorbent. This will be property number 3, I guess. Is balanced. Okay. In other words, let V belongs to M. So we have a vector in M. And alpha in R such that the absolute value of alpha is less or equal than 1. Okay? So remember, if alpha is only positive between 0 and 1, so alpha v belongs to M because of the convexity. You have 0 and you have v, so you have the segment 0v inside M, and this will give us from the convexity will give us that alpha v belongs. But now we're taking alpha negative. So in particular, so here we have P of alpha v equal to absolute value of alpha pv, which is less than pv, which is less than 1. And therefore, so alpha v belongs to M. So not only we have alpha v for alpha between 0 and 1, which is the convexity, no, but we do have it between 0 and minus 1. And one way to see this, in fact, is the fact that we are, if we show that minus v belongs to M. So in other words, if v belongs to M minus v, the symmetric one, belongs to M, then of course the entire segment minus v will be in M because of convexity, which is exactly the same conclusion as we have here. So we say that M is balanced. Using the two properties together, then we have, okay, using property 1 and 2, using convexity 1 and 2, we get for any alpha beta such that absolute value of alpha plus absolute value of beta less or equal than 1, and any v1 v2 in M, then alpha v1 plus beta v2 belongs to M. Next, still under the property of absorbent, let V belongs to V such that P of V is not equal to 0. Because if it's equal to 0, then V belongs to M, okay? Not equal to 0. So in this case, P of V will be positive, not equal to 0, okay? Let alpha equal 1 over 2 times PV, okay? Then P of alpha V is equal to absolute value of alpha P of V from the property number 2 of homogeneity of the seminorm, which is exactly 1/2 less than 1. So alpha V belongs to M. Okay? And that is the property of being absorbent. So to be absorbent, so we say M is absorbent. Okay. Note that V, in fact, is the union of alpha M when alpha is positive. Okay. Okay. Because of this absorbent business, so V will be the union of all the alpha time M for alpha's positive. Okay. Let us here say there is some kind of converse to this, and Minkowski is the one who investigated this. Let me just say what it is exactly. So here, remark. Let me put as a remark here. Let C be a subset of V, which is not empty, such that C is not empty. C is convex and absorbent. So in other words, we have M, I'm sorry, not M. We have V to be the union of alpha C, alpha positive. Okay? Then we can consider the function PC defined from V into 0 plus infinity, okay, such that PC of little v equals the infimum of alpha, such that v belongs to alpha c, which is exactly the same as the infimum of alpha, such that 1 over alpha times v belongs to c. Okay? So PC will satisfy property 1 and 2. 1 will satisfy property 1, 3. Okay? The problem with 2 is that what we have is for 2 of the seminorm, of course, property 2, we will have PC of alpha v equal alpha PC of v for alpha positive. So in order to catch alpha positive or negative, we need to have that if C must satisfy the property that if V belongs to C, then alpha V belongs to C, provided absolute value of alpha is less or equal than 1. Okay? Or less than 1. If you C is open or closed, in other words. Okay? So here, what happened is that if this is true, then 2 is true. Then 2 will be satisfied. Okay? And in this case, the set of V such that PC of V is less than 1 will be included. Oh, I'm sorry. Let me erase this. In this case, we have C, which is included in the set of V such that PC of V less or equal than 1 and contains the the open ball PC of V less than 1. Okay? So the set C is in between the open and the closed balls or P-balls associated to P. The function PC is known as the Minkowski functional associated to C. So whenever we take a convex set which is balanced and has this kind of symmetry property, automatically through the Minkowski functional we generate a seminorm. So the family of seminorms are I mean are we do have a lot of them. That is exactly the point I'm trying to make here. And for example, one can wonder, when do we have the balance? And people have investigated Minkowski functionals in the case of vector spaces when we have no norm in the absence of known norms. Okay, so let us a little bit investigate in details this issue of topology. Okay, so so the topology generated by these seminorms defined on a vector space. And let me just I want to focus on And the reason is, as we said from the beginning in the welcome video, that the problem is sometimes we want to approximate solutions of functional differential equations, and we want to have some kind of convergence of sequences, and that's why you need to have a problem with the limit of sequences. We want to go back to some kind of convergence of sequences. So in this case, as we said, we will assume that we have a vector space, and on that vector space we have this seminorm P. From the seminorm P we can define this topology, and we said because it fails property number 1, so we don't have a host of topology. Okay, so that is the problem. So what we are going to do is assume that you have a family of, so here let V be a vector space. Okay, and let P lambda be a family of seminorms. Okay, a family of seminorms. So we can form the P-balls, okay, associated to each P lambda, and we define the topology. So in order for us to define topology, we need to define an open set, and we'll say that, so definition, we'll say that O is open if and only if for any V in O, okay, there exists lambda 1, lambda 2, lambda n in gamma, okay, and epsilon positive, such that the intersection of the open balls centered at V with radius epsilon is in O. Of course, here the notation, because we did not introduce this notation before, where B lambda O V epsilon is just the open ball as defined before for a seminorm W in V, such that P lambda of V minus W less than epsilon. Okay, so this defines the concept of open set, and what we can prove is that, as usual, the empty set is open, so one can prove that, okay, any union of open sets is open, and any finite intersection of open sets is open. Okay, clearly the empty set and the entire space are open. Also, the empty set and V are open, and so we have a topology. So we have a topology V T. Okay, so this topology now is defined from the P lambdas. Still, Okay, this topology may not be Hausdorff. So whether we have one or we have this, the one that we talked about before, but this topology is not going to be Hausdorff. So in general, this topology is not Hausdorff. So in other words, it doesn't separate the elements. Okay, you cannot find if U is different from V, that there is an open set around U and an open set around V, which with empty intersectional, just disjoint. So this may not be the case, but for practical purposes, if we assume that the family P lambda, okay, has the separation property, as discussed before, then in this case, this topology is Hausdorff. Then is Hausdorff. So we do have a nice topology on V, and we will say that V is a topological vector space. In short, okay, in short, we'll use V is a TVS. So it's a topological vector space. So you see, what's interesting here is the fact that a norm defines a topology natural from the distance. Seminorm do not, because I mean you can have a topology, okay, but it's not a Hausdorff topology. It does not separate because we fail to have P of F, P of V equals 0 implies V equals 0. And now what we do in some cases, when you have a family of seminorms that has this separation property, then the topology generated by all of them, is a Hausdorff topology. Okay? And what happened when the family is countable? This is very interesting, as we saw in the introductory example. Okay? Countable family of seminorm that has the separation property. So here's special case. Let Pn be a countable family of seminorms defined on V with the separation property. Okay, that's exactly what happened in the motivating example that we started with this web note. So in this case, what happened is we can have, it's very interesting, we can have first, okay, note before I go to the next one. And the people who still remembers their course on real analysis with measure theory would understand what I'm going to be doing next. It's similar, we have seen this before in the space of measurable functions to show that there is the topology of almost everywhere convergence, that it is metrizable, that there is a distance that gives you that convergence. Same idea here we are following, okay? So this is how it goes. First, let me say something before I go and show you this result. Fix P, which goes from V into 0 plus infinity, be a seminorm. Define P star from V into 0 plus infinity by P star of V to be P of V over 1 plus PV. So this one, this P star, we have seen something similar in metric spaces. if you have a distance, you can generate a new distance using the same property. And the reason is because the function f of t equal t over 1 plus t is subadditive. Okay? It's subadditive, and that's why it allows for a new distance. Okay? So here, what are the properties of P star? P star is no longer a seminorm. But what happened is the following. So what do we have? We have number one, that's P star of V of 0 is equal to 0. Number two, P star of plus minus V is equal to P star of V. Number three, P star, the triangle inequality. So this is true, okay? Okay, so, and of course, P star, this is very important, of V equal to 0 if and only if P of V is equal to 0. Okay? So we have the triangle inequality. We have some kind of symmetry here, but we fail to be homogeneous. We lost that. Okay? So now back to our sequence, back to Pn. So what we will do, okay, we introduce, let's call it P star. We define P star from V into 0 plus infinity by P star of V to be the sigma of 1 over 2 to the power n. And here we have P star n of V from n equal 1 to infinity, which is basically sigma 1 over 2 to the n Pn V over 1 plus Pn of V. So what's interesting is that this series is very well defined. It's absolutely convergent regardless of the V. Okay, so because they are all less than 1, the P stars are all less than 1. That's why we took this new functional P star. So we have P star of V less or equal than sigma of 1 over 2 to the n. So we are using the convergence of the series 1 over 2 to the power n. Okay, so P star is very well defined. Okay, and what are the properties of P star? Okay, so properties of P star. So clearly we do have P star of plus minus V equal P star of V, number one. We do have also, because of the subadditivity of the function, we do have the triangle inequality. Okay, what's interesting here is the property number one, which is that what happens when V is equal to 0. So if this is true, this happens if and only if every one Pn star of V is equal to 0 for any n, which is true that this implies Pn of V equal to 0 for all n's equal to 1. So if we have the separation property, okay, if the Pn's, they have, the sequence Pn's has the separation property, then we will get that P star of V equals 0 if and only if V equals 0. So be very careful. P star is not a norm. Okay, it's not a seminorm because we failed the homogeneity, but it has these three properties, very important. So this P star will allow us now define, this is truly amazing, D from V cross V into 0 plus infinity, defined by D of uv to be equal to P star of u minus V. Okay? And what's interesting is that, so again, let me just give the expression for for d of uv using the pn's, because I don't want people to be confused with d stars, is sigma 1 over 2 to the n p of u minus v over 1 plus p of u minus v. And this is n from 1 to infinity. Pn, sorry, Pn. So you see, d now becomes a distance. So we have d, so number 1, d of uv equals 0 if and only if u equal v. Of course, I'm assuming that we have the separation property. 2, d of uv is the same as d of vu, and this is where we're using plus minus. And finally, of course, we have the 3, the triangle inequality. duv is less than duw plus d of w. So we have a distance, okay, a real distance. And now that we have a distance, we have, so this v, the vector space, becomes a metric space. And if v becomes a metric space, then we can define, as we did before, a topology. So let S be the metric topology generated on V generated by D. Okay? So here, again, okay, given this family, this countable family of seminorms on V with the separation property, we're able to come up with the topology T, which is Hausdorff. And now, tweaking around these PNs, we are able to build a distance which allows for a structure of metric space on V, and then we have now a natural what? Topology S, which will be known, as we said before, the strong topology. That's why I choose S, on V generated by this distance. Okay, and the beautiful result here, okay, theorem, beautiful result. So both T and S are identical, and this is really beautiful, identical. So in other words, an open set for T is the same as an open set for the S topology defined by this distance T. And in particular, closed sets for T can be characterized by sequential conversions because we are in a metric space. Okay? So in this case, we say that the topology T, which really was not clear to us, is metrizable. In other words, there is a distance that generates this topology. A beautiful result. Okay? Okay, note, okay, that if we fix a vector u in V and alpha in R, and let us consider T sub u, which is translation basically, from V into V by V gives V plus u, and M u, the multiplication by, I'm sorry, not u, alpha, from V into V, from V gives in alpha times V. So both functions, okay, Tu and M alpha are continuous. Okay, this is true whether you are metrizable or not. Once you have a topology T for the family P lambdas, these two vector functions defined on V are both continuous, which means that the addition and the multiplication by scalar are continuous, which by the way is not very hard to prove in the case of the PNs and in the case of the distance D that we defined above. Okay. So conclusion, whether when we have a vector space, if we have a norm, we have a structure of metric space, and therefore we can use all the properties of the norm. But if we have a family of seminorms, we have a topology, and if this topology is Hausdorff in the case of the family of seminorms, which are which have the separation property, then we have a topology which infers to the vector space a structure of topological vector space, TVS. And finally, if the family of the seminorms which has the separation property is countable, okay, then in this case we have that topology T is metrizable, and we can define the distance that will give us the same topology. And so we can work with the distance and the conclusion in terms of convergence and all these properties of topological properties will be identical by using the distance T, D. Thank you.